underground, these miners chip away at solid rock. Chunks of ore are carried out of the mine on belts and refined into the pure mineral gold. People dig for rocks and minerals all over the world, from gemstones in Australia to coal in North America. To find out what rocks and minerals are and how they form, we're going to travel with an earth scientist, Steve Kluge. We'll see some of the building blocks of the Earth's crust and find out how they're transformed into the many rocks of the world around us.
This is an abandoned quarry. 75 years ago, people were mining here for materials used in the manufacture of ceramics. When they finished, they left us with this slice in the earth, a good place to study geologic processes. Of course, this slice isn't very deep. It really represents only a scratch into the Earth's crust.
The crust is the Earth's brittle, rocky outer layer. It's only a thin skin riding on the hot plastic inner layers, but it's from this thin skin that we get all of our rocks, minerals, and resources.
This old quarry is a good place to start learning about the Earth's crust because several basic Earth materials occur here in relatively pure form. These materials are called minerals, and they're easy to pick out here. This is quartz, this is feldspar, and this up here is a mineral called mica.
Minerals form as individual atoms bond together into an orderly, repeating, three-dimensional structure. These structures are what we call crystals. Once a crystal forms, it will keep growing, adding more new atoms to its orderly pattern as long as conditions allow.
As we can see from these models, each mineral has its own specific crystalline structure. This is a model of the mineral calcite, and this of fluorite. This unique arrangement gives each mineral its own specific physical properties. Some of them are easy to see. For instance, if we talk about color, we can see that the quartz is white, while the feldspar is pink. The quartz is also very hard, whereas the mica is soft and flaky. We can define a mineral as a crystalline solid that occurs naturally in the crust of the Earth. Geologists have identified hundreds of different minerals, but only about 40 occur commonly in the rocks around us. We can identify minerals by testing them for their physical properties. We'll take a look at the way geologists test for some of these physical properties. The first thing you might notice is that minerals are many different colors, not just pink and white. This pyrite is so yellow and shiny, it's often called fool's gold. This amethyst is a deep purple, and the bornite is multicolored. We can check the color of a mineral in another way, too. These two samples seem to be the same color, a shiny gray. But if we rub each on this white tile so that a little bit of dust comes off, we get a much different picture. The color of this powdered mineral is called the mineral's streak. If we look closely, we see that minerals are different in a couple of other ways, too. This one here is silver and shiny, almost like metal, whereas this one is dull and earthy. The way that a mineral reflects light is called its luster. And you can see that different minerals have different lusters. Just by looking, we've already divided the minerals into several different categories. Different colors, different streaks, and different lusters. Now let's compare the minerals to see how hard they are. We usually think of all minerals as being very hard, but some are not as hard as others. For instance, this mica is so soft that I can scratch it with my fingernail. This mineral is harder. My nail won't make a mark on it, but I can scratch it with a steel file. This quartz is even harder. It scratches my thumbnail, it'll scratch this mineral, and in fact, it's so hard that it'll scratch the steel file. The next test you would do to identify a mineral is to break it. I'll show you why. When we break this mica, we get thin, flat sheets. If I break it again, more thin, flat sheets. Every time. Now let's break this one. It didn't break into thin sheets, but each piece is the same shape as the original. If I break it again, the pieces are smaller, but they're still the same shape as the original. The way that a mineral breaks is called cleavage, and many minerals can be identified by their cleavage. This is because the way a mineral breaks is determined by the arrangement of the atoms in its crystal. The shape of this model of calcite is reflected in this crystal.
Cleaving minerals is one step in preparing gems for jewelry.
Color, streak, luster, hardness, and cleavage. These are all simple tests that help us identify minerals. But minerals usually don't occur in their pure form. More often we find them together with other minerals in a solid mixture called a rock. Rocks can be formed in several different ways. We'll visit some places to see evidence of what some of those processes are.
Originally, the Earth was a ball of fiery liquid called magma. The first rock formed as this magma cooled and became solid. This is called igneous rock, because ignis is the Latin word for fire. There are still places deep within the Earth where temperatures are hot enough to melt rock into magma. Sometimes the magma is forced up into cooler regions.
When they made this road, workers cut a slice through rock that was formed in just this way. Igneous rock. Let's take a look at it. The rocks in this wall formed deep within the Earth hundreds of millions of years ago. It formed when the magma began to cool. Tiny crystals of several different minerals formed and grew until they ran out of room. This is the result, an igneous rock called granite. Like all igneous rocks, it's a random mixture of interlocking crystals. We can see crystals of some of the same minerals that we saw in the quarry: feldspar, quartz, and mica. Almost all igneous rocks are formed this way, but not all igneous rocks look alike. The differences we see tell us more about how the rock was formed. For instance, some rocks may be formed of different minerals. This gabbro was formed from minerals that are rich in iron and magnesium, formed from a magma very different from the magma that formed the granite. Another thing we can easily see is the size of the crystals, what geologists call the texture. There's a good sized crystal of mica right in here, and you can see some very large feldspar crystals throughout the rock. The quartz shows up over in here, another large crystal. These crystals are large enough to see with the naked eye. This igneous rock is called rhyolite. It's made of the same minerals that the granite is made of, but the crystals are almost too small to see. This tells us more about how the rock was formed.
Sometimes the magma pushes clear through to the surface. As the magma reaches the surface, gases and water escape from it, and it changes its nature somewhat. So we also change its name. It is now called lava. The lava may build up a mountain we call a volcano.
The lava cools to form rock so quickly that the crystals don't have time to grow large. That's how this rhyolite was formed. It cooled very quickly, and the crystals had no time to grow. The granite cooled very slowly, so it has large, easy-to-see crystals. The two look very different, but the only real difference is the time they took to cool. All of the original rocks of the Earth's crust were igneous rocks, just as these are. But those original rocks were formed billions of years ago, and since then have undergone many transformations into many different kinds of rocks. We'll take a look at some of those transformations.
After rocks have formed, water, wind, and ice can very gradually scour and grind them into small particles, like sand and silt. These particles can be carried by moving water through streams and rivers, and finally into the sea. There, the particles, called sediment, settle to the bottom and build up layers. As the layers become thicker, they are compressed and cemented into rock. This is called sedimentary rock. If a layer is made up mostly of plant material, it may turn into coal. If it's made up mostly of chemicals or salts, it may be compressed into limestone. If it's a layer of weathered rock particles, it will likely look like this.
The most striking thing about this rock is its layers, the horizontal beds of sediment deposited millions of years ago. Because of the way it was formed, we call this rock sedimentary rock. You notice that the layers are very uniform. They stay about the same thickness for some distance, and here each layer is made of almost the same material as the next. Most sedimentary rocks are made of particles that have been cemented together. In this case, the particles are so small that they're hard to see with the unaided eye. In other rocks, the particles may be the size of pebbles or even small boulders. Sometimes you can find the remains of ancient animals that were trapped in the sediment as it was compressed into rock. This is called a fossil. The sediments that formed these rocks were deposited, buried, and compressed deep within the ocean. Over millions of years, geologic forces raised them to their present position, part of a mountain range high above sea level.
It takes great forces to raise rock out of the sea, bend the layers and tilt them, and make them into mountaintops. These same geologic forces also work deep in the crust. There, great heat and pressure break and realign the atoms of the mineral crystals. This creates a new structure, a new mineral.
The result is a rock like this. It may once have been an igneous or a sedimentary rock. And then, deep within the earth and at great temperatures, pressures were exerted on the rock like this. The bands that we see here are the new minerals that formed under that great heat and pressure. We can see that this rock has alternating bands of light minerals and dark-colored minerals. We can see that the bands in this rock are not nearly as uniform in color or thickness as the layers we saw in the sedimentary rocks. This rock is called gneiss. It's part of a larger class of rocks called the metamorphic rocks. Metamorphic means changed form, and we can see why. Hundreds of millions of years ago, it may have been like the granite we visited earlier, or like the layered sandstone. But it was changed under great heat and pressure into a very different kind of rock. The Earth's crust is a complex and constantly changing environment. Its basic building blocks are the minerals. We usually find minerals in solid mixtures called rock. But even rock is not permanent.
There are three things that can happen to any rock. It can be melted and then cooled to form a new igneous rock. It can be weathered, deposited, and compressed to form a sedimentary rock, or it can be changed by heat and pressure into a metamorphic rock.
Through these processes, sometimes called the rock cycle, the minerals of the Earth's crust are constantly changed and transformed into all the rocks that we see around us.
Traveling with Steve Kluge has been more than just an exploration of some rock outcrops. In a sense, it has been a journey into the heart of the Earth, where individual atoms join together to form minerals, where minerals interlock in rocks, and where rocks themselves are changed and transformed over the millions of years of geologic history.